Hey everyone. A few people have asked if I could record a video discussing how to fit and assess multiple models, and in particular, how to take a fitted model and apply it to an evaluation set. I'm not going to do that with the competition data that you're working on. So I think this semester students are working on used cars data, but instead I did find a Kaggle competition on predicting Airbnb listing prices in New York City. So that's the data set that we'll use here. It's a competition that's closed now, but we'll be able to submit to the leaderboard if we want and see how well or how poorly we do with respect to the people who competed in this competition at the time. They're using kind of a funky error metric for scoring their competition. We're not going to worry about that. All you need to know is that in addition to things like the root mean squared error, the mean absolute error, we can define other scoring metrics that we want to optimize over. This is something called root mean squared logarithmic error, beyond the scope of our course, but again, worth knowing that there are other error metrics that we could consider. So the data that we're working with, I'll show you has a bunch of different columns. Basically, we are interested in predicting the price, so the cost for one night of booking the listing. You'll notice that this price column is present in the training CSV file. So if I select all of these and apply that filter, we should be able to scroll off to the right and see that the price column is available here. If we look at the test file, this is what we've been calling the eval file or the eval data set in our course. These are all of the observations that Kaggle knows the answers to, but we don't, and we're trying to predict the price for the properties in this data set. And you'll notice as we scroll off to the right, the price column is missing here. So we have no way to recover it other than to build a predictive model. Again, Kaggle knows the answers. So what we'll do is we'll use our model. We'll build several of them to try to identify a best model. We'll use our best model to make predictions, and we'll upload them to Kaggle to see how we did. So I've already downloaded the data files here. They're in my downloads. I've unzipped them, so I have access to train, which is, again, all of the observations that we have access to the price column with. Test is what we've been calling the evaluation data. These are properties that we don't have access to the price for, and we're tasked essentially with building a predictive model to predict price for these properties. And then we do have access to the sample submission file, which will show us what Kaggle expects the submission document or submission CSV file to look like. I've just started sketching out a notebook for us with an outline. There's no code in here yet. We'll populate the code just shortly. I'm connecting to an instance, and let's upload the data, and then we'll get started. So I'm going to upload all three files just in case you want to see what that submission file looks like later on. So all of the data files are uploaded here. Let's get started with our imports. This is pretty familiar at this point. We're going to import pandas as PD, which will allow us to deal with tabular data. That's what we're dealing with here. We're going to import NumPy as NP, just in case we want some mathematics functionality. We'll import matplotlib.pyplot as PLT and import Seaborn as SNS in case we want to do some data visualization and plotting. I think for the most part for this notebook, I'm going to avoid that because what people have asked me for is a focus on model construction, and in particular, applying a fitted model to an evaluation set. So while we're reading those packages in, we're probably not going to use them. We are going to import some modeling functionality here, though. So from sklearn, .model selection, let's import train test split and cross val score. So train test split we know is useful for splitting our data set up into random partitions. Cross-val score implements this cross-validation technique. Cross-validation is really useful for us because it helps us estimate a more stable performance estimate for any models that we build. So we'll optimize our models in this notebook for root mean squared error, which is what we're used to in our class. But again, there are other error metrics out there, and in particular, this competition whose data we're working with is focused on a different error metric as well. So we're importing that functionality to split our data and then to kind of give us a less biased approximation for expected model performance. And then we'll also import some model building functionality. So let's say from sklearn.linear model, we'll import linear regression. And then from sklearn.linear model, let's not do linear model, let's do tree, import decision tree regressor. And there are other model classes out there as well. So maybe let me show you one from sklearn.ensemble, import random forest regressor. So random forest will be a collection of trees. I'd encourage you to look more into this type of model. It's really interesting how it works. But we build a collection of trees on different versions of our data set. And at each point where the tree gets to ask a question, it only gets to look at a random subset of the predictors. This is so that the trees don't look similar to one another, and it actually ends up giving us very differently looking trees. And there's a real advantage to that in terms of predictive accuracy. So we may also look at this random forest regressor. So we've got a few models to look at. We can also vary the models even just within a model class, like linear regression, by just varying the predictors that the model gets to look at. So we'll do that here as well. Now that we have all those modules loaded in, let's load up our data. So data equals pd.read CSV, and we're going to read in train.csv is what our file was called. And then let's say eval equals pd.read CSV, and that's going to be test.csv. And then once this is all read in, let's look at data.head so that we can see what we're working with. Okay, so that seems to have worked. We've got the data in here. We see all of the columns that we saw on Kaggle. In particular, we see this price column. Again, that's the thing that we're trying to predict. This is the price for booking a one-night stay at an Airbnb property in New York City. And we have access to a bunch of different features which may be useful in predicting that price. Again, I'm going to change the number of observations we're looking at here just so that doesn't clutter up our notebook. Okay. Before we go into actually modeling our data, it may be worth looking at a data quality assessment. So this involves just kind of making ourselves aware of any problems we may experience with our data, such as the presence of missing values. So let's do that now. One way we can do this is by looking at data.info. So in data.info, we see we have 34,226 rows of data that we're dealing with. These are properties. For the vast, actually not for the vast majority of these columns, we have some missing data that we should be worried about here. So this is one of the first times that we've encountered that beyond the initial heads up. Here's what a modeling task might look like, notebook and video. So let's see what we can do with missing data here. So what I'm going to do is run data.isNA.sum. This will give us a heads up as to where the missing data in our notebook kind of is, where it appears. So it looks like we're missing 9 entries underneath name. We're missing 14 entries underneath post name. And we're missing 7,008 entries underneath last review and reviews per month. So I think luckily we can make some assumptions here. We're probably safe to fill in the name for these 9 people with something like unknown, or these properties, I should say. So the name of each of these 9 properties we can fill in with unknown. The host name, similarly, for those 14, we can fill in with unknown. So let's do that now, and then we can talk about the last review and the reviews per month. So what we'll do is do something like data name, where let's say data name dot is NA. We run this, we should just get a bunch of missing entries. Yeah. So name is not available for these 9 entries. What we can do is in here, fill in those values with unknown. And if we run data.info now, we should end up with no missing values in that name column. Perfect. And maybe a better way to see this is data.isNA.sum. Now, again, there are no missing name values. What I'm going to do, just to keep this kind of clean, is also do the same thing with host name. So data host name, where data host name dot is NA. We're going to fill that in with unknown as well. Now, if we run this again, no more missing data in the name or host name columns. The only thing we have left now to worry about is where last review and number of reviews per month kind of appear. To me, I think I'm going to make the assumption right now that these are properties that have never been reviewed, and that since they've never been reviewed, their number of reviews per month, maybe we can say is 0. And their last review, we'll look at what the column contains and then kind of make a decision there. So let's take a look at data. Last review and reviews per month. So we're only going to look at these 2 columns. And let's look at the first 5 rows there. Okay. So it looks like last review is a date. And reviews per month is a number. In this notebook, we're probably not going to use a date column, the last review date column at all, just to keep it kind of simple. Reviews per month we may use because it's kind of a nice predictor. So let's go ahead and say data last review, where data last review is NA. I'm actually just going to drop in today's date. So 2022-06-24. This is probably a poor decision. We could do better than this if we wanted to dig more into the data, but again, we're probably not going to end up using that column. So let's just fill it quickly and move on. And then also now reviews per month. So data reviews per month, where data reviews per month dot is NA. Let's fill those in with 0. These are properties that have never been reviewed. This is a really simplistic approach. It's putting these properties at potentially a disadvantage. They've never had a chance to be reviewed if they're new, which is what we're conjecturing. But again, for the purposes of this notebook and video, this is probably an okay decision for right now. Let's run data.info after doing all this, just to see whether we filled in all of the missing values. And instead of data.info, let's run isNA.sum, which will show us a more compact view. And now we can see no missing data. So we've kind of fixed all those issues. We've taken the easy route. And again, like I said, potentially there's some better feature engineering, or actually imputing is what we would call what we just did. Some better imputing decisions that we could have made. But for now, the quick and dirty approach, this will be good enough. So at this point, we've got our data. We've kind of solved all of the data quality problems that we've identified just by looking at .info and for missing values. There are potentially some other problems that we could come up against. In particular, I think this neighborhood group column may be a good column to use. So I'm just going to show you data.head again. The neighborhood group contains things like Manhattan, Brooklyn. This is a categorical column that probably has pretty few categories. And so perhaps this would be a nice categorical column to use in a model. There may be some association between the location of the property in terms of these neighborhood classifications and the price per night. So one thing that we could look at there is just to see data, neighborhood group, and then .value counts. What I'm looking for here is to try to determine whether there's some neighborhoods with really infrequent counts. There's clear imbalance here. So Staten Island only has 249 properties in this data set, where where Manhattan has over 15,000. But there are no real like straggling properties with just or neighborhoods with just one or two observations. So I'm going to move forward with this. This should be okay. There are techniques where if we really thought that this neighborhood grouping was going to be a super beneficial factor in predicting price per night, we could upsample, which means kind of generate new observations from these minority neighborhoods to make them kind of match or have the same representation as the larger neighborhoods. But again, let's not get into that. The other thing we could do is just look at the neighborhood column. Here we'd get into trouble because we have some neighborhoods listed with singletons. So neighborhood, if we wanted to use that, we would need some tricks for this, like grouping all of these singleton and low property neighborhoods into potentially an other category. But again, we won't get into that in this notebook. So things that we're going to do in this notebook is we'll probably use neighborhood group as a predictor to show how categorical predictors work. We're going to avoid just the neighborhood predictor because of those problems with singletons and kind of low property neighborhoods, so where they don't have a lot of representation in the data set. Perhaps we'll do the room type. So looking at room type here, the value counts there. This will be another good categorical predictor that we could use for our model. I'm not saying that it's going to have high predictive value, but it's going to be one that's kind of easy to implement in a model. We have minimum nights, which looks like a numeric column. Number of reviews is a numeric column. Reviews per month is numeric. Calculated host listings count, so the number of properties the particular host has on Airbnb listed for rent, that will be a numerical variable. Then we have availability 365. This is kind of an interesting column because it ranges from 0 to 365 days in the year. We may want to scale that. I'm not sure if we would observe anything beneficial from like scaling it down to a percentage from a raw integer value of nights. So we'll potentially look into some of these things in this video. I don't want to make it too long, but we have lots of ability to explore some different types of models. Data preparation, one thing I want to do here is I want to get rid of the columns that we're definitely not going to use. So here in the training portion of this notebook, we are not going to use columns equals. I'm going to call this data reduced so we don't kind of obliterate columns in our original data set in case we decide we've made a mistake. But I'm going to get rid of the ID column. The ID is a random ID assigned to the listing. There's no reason that should be associated with the price per night. I'm going to get rid of the name of the listing. There's potentially some value there. Some people will read the name of a listing, and if it's named well, be attracted to that. The host ID is a random identification number applied to the host. Let's also get rid of the host name. We're going to keep the neighborhood group. Let's get rid of the neighborhood. Remember that had some issues there with neighborhoods that had just single properties listed or very few properties listed. Latitude and longitude we can keep. Room type we'll keep. Price we're going to keep because that's the quantity that we want to predict. Minimum nights we'll keep. Number of reviews we'll keep. Last review, let's drop it for now. As I said, we're probably not going to use that column. It potentially would be useful, but in the context of this notebook and video, let's avoid it. Reviews per month we'll keep. Calculated host listings we'll keep. And then availability we'll keep. So let's just drop all of these columns. Because we want to drop columns, we're going to have to say the axis that we're dropping from is 1. By default, again, the .drop method will drop rows instead of columns, and we'll get a complaint saying that none of these items were found in the axis that we're trying to drop from. So let's do this, and then let's call data reduce.head and see what we ended up with. And so now we can see that we're only left with the columns that we didn't drop. So we have neighborhood group, latitude, longitude, room type, price, minimum nights, number of reviews, reviews per month, calculated host listings count, and availability 365. One thing that you may do at this point is also reduce the evaluation data set. Since we're only using these columns for model construction, we're not going to be able to use any of those additional columns that we dropped when we try to apply the model to the evaluation data set. So let's drop those as well. So I'm just going to copy the first line here, and I'm going to call this eval reduced. We're going to say eval.drop. The only thing I'm not going to drop here is ID. And the reason for that is because we need the ID column when we go to build predictions. But because we're calling this eval reduced and we're not overwriting the original eval data frame, let's actually drop that. We're fine to do it. Keeping it would cause some headaches later, and we can always recover the ID column from the original eval data frame. So let's go ahead and drop it. Okay, now the data reduced and eval reduced data frames have nearly the same columns. Data reduced has the price column, eval reduced doesn't, but otherwise they have the same exact columns. And now we're going to want to do a train test split. So let's say train test equals train test split. We're going to split the data reduced data frame. And in fact, actually, before we do this, because we're focusing on model construction only and not any data visualization or exploratory analysis, let's get dummy variables for the categorical columns that we've kept here. So we've kept neighborhood group and room type, our categorical variables. Let's grab dummies for those. So data reduced dummies equals pd.getDummies, data reduced columns equals, and now the columns we're getting dummy variables for are neighborhood group, and we're going to need to pass this in the form of a list, so we'll use square brackets for that. So neighborhood group and room type. And we're also going to pass the drop first argument true. Since we're doing this with the data file, so with the data we're going to build our model with, we should also do it with the evaluation data as well. The evaluation data is going to have the same columns that, so I should say, after we fit our models, we're going to have to provide the same columns from the evaluation data that the model was fit on to the model in order to generate those predictions. So getting these dummy variables and dummy columns now is going to be helpful to us later. So eval reduce dummies equals the same thing, pd.getDummies, eval reduced is the data frame that we're working from. The columns we're getting dummies for are neighborhood, group, and room type. Again, we're going to drop first. It's true. And now let's just print out data reduced dummies.head, and let's see what we're working with. So we have a columns, and I need an equal sign between there. Perfect. Okay, so now we can see that instead of having a neighborhood column, we've got dummy columns in place of this. So neighborhood group Brooklyn, Manhattan, Queens, Staten Island. Room type, similar idea. All right, so we're ready to go ahead and start with model construction. Again, well, actually, no, we're not ready to go ahead with model construction because we haven't split into training and test data yet. So let's do that now, and then we'll be ready to move on. So train and test now is going to be train test split. We're going to split data reduced dummies. The training set size, let's say, is going to be 80% of our observations. And the random state we're going to use is, let's say, 570. And then let's look at train.head. What we should see is that these indices are mixed up. Remember, train test split shuffles our data. And we will no longer have all of the data just in the training set. Some of it will be set aside for the test set. The training set will contain 80% of our rows. The test set will contain the other 20% of our rows, and there will be no rows shared between those two sets. The columns are the same between the two data frames, though. All right, so now we're ready to go forward and do some model construction. So what we're going to start with here is just a model that has a single numerical predictor. Let's do maybe the number of reviews per month is the only numerical predictor. So number of reviews per month is the only predictor to predict price. So let's say now X is equal to train. And the column we want is reviews per month. And then Y is going to contain the thing that we want to predict. So this is going to be train So we have now X as a data frame of the predictors that we're allowing our model to see. This is the information that our model is going to get to use in order to try to make predictions and get about the price value. So we're not allowing our model to have lots of information here. We have a really rigid model. It's not flexible. Let's define linreg equal to a linear regression model. And what I'm going to do first is I'm just going to fit a linear regression model the way we have been up till about a week ago. So fitting it on the training data and then assessing it on the test set, because I want to make a point about training, about the validation set approach versus our new approach called cross-validation. So let's fit this model, linreg.fit on X and Y. What this is going to do is it's going to get an intercept coefficient and a coefficient on price, a coefficient on reviews per month, and it's going to build that model to predict price. At this point, we'll be able to build predictions. So I'm going to get predictions on both the training data and the test data. So let's do this. Preds train is equal to linreg.predict. And what we can do is predict on, I want to make this explicit, train views per month. And then Preds test is going to be linreg.predict test views per month. Now, the only difference between these two lines of code is that the first line, we're making predictions on the training data. The model knows what the answers are. It knows what the prices of the listings are for the properties in the training set. So it has an advantage in these predictions. And then in the second line, or the last line here, we're making predictions for the properties in the test set. The model didn't even know that these existed, so there's no advantage that the model has in predicting the booking prices of these properties. So at this point, we can look at estimating our error rates. So we can print something like the training root mean squared error, and we're going to have to calculate that. So what we'll do is train price. So this is the correct answers. It's the true prices for a booking minus Preds train. Those are the predictions that our model makes at the booking prices. And we're going to square the differences after we compute them. Once we've squared those differences, we're going to take the average. And then once we take the average, we're going to have an average squared difference. We don't want that difference in terms of dollars squared. We want that difference in terms of dollars again. So we'll take the square root in order to get back down to a meaningful unit. That will compute the training RMSE. And then we can likewise compute the test RMSE. So we'll go through this line again, test RMSE. What I'm going to do is I'm going to take the correct prices as listed in the test data set. I'm going to subtract away from those the predictions that our model made for the prices of those properties. I'm going to, again, go through the computation of the root mean squared error. So I'll square those differences, take the average, and then take the square root. This will give us a training error metric in terms of root mean squared error and a testing root mean squared error. And let's see how our model does. And so we can see that our model doesn't do super well. The training root mean squared error is around $222 a night. The testing root mean squared error is around $277 a night. If we look at something like train price mean, the average price of a booking is only $151. So we're way off here. This training RMSE is quite bad. Okay, so what can we do? We know this model is bad. So how do we improve on it? We move to potentially adding other predictors, um, using predictors instead of the reviews per month. But before we do that, I want to talk to you about the difference between this validation set approach and cross validation. These are not different models, but what cross validation does, the cross validation simply provides a better estimate of the expected prediction error. So we're not getting a new model. We're simply saying um, that these error estimates, and in particular this one, the test RMSE, could change quite a bit if we got a different test data set. And so um, let's use cross-validation to build several models, compute the test error for each of those models, and then average those test errors together, which will give us a more stable error estimate, a better approximation of the true prediction error if we did use this model, a linear regression model, which only used reviews per month to predict price. So again, we're not changing the model at all. We're just getting a better estimate for its prediction error. So how do we do that? So it's not a whole lot different, to be honest. So again, just to be explicit about this, let's say X is trained and its reviews per month is the only predictor we're allowing our model to see, and Y is trained. And linreg is linear regression. So up until this point, this is the model definition. We're building a linear regression model. That model is going to be allowed to see the reviews per month column as it tries to make a prediction on the listing price. What's changing now is how we're estimating model performance. Again, it's not a different model, it's just a way to better approximate the prediction error. So what we'll do is define a new object called cross-val errors. We're going to use cross-val score. Cross-val score is going to take our model, that's called an estimator. So linreg is the model. It's going to take the data frame of predictors that the model is allowed to see. That's stored in X. Right now, it's just reviews per month. It's going to take the true responses corresponding to those observations. That's Y. It's going to take cross-validation folds, let's say 10 folds, and then it's going to take a scoring parameter. What I'm going to do is just put this on a new line so it's easier to read. What we're going to do is score according to negative root mean squared error. This is related to the root mean squared error that we're used to. So same root mean squared errors we estimated above. The negative in front here, just it's an artifact of the way this um, uh, the mathematical algorithm behind linear regression likes to optimize the coefficients. It prefers to deal with maximization rather than minimization. So that's why we're dealing in negative numbers. But once we have this, we can print out the cross-validation errors. So this is going to be the root mean squared error on each fold. So I should get 10 root mean squared error estimates. So I'm going to take -1 times cross-val errors. Again, -1 there only because I want to kind of cancel out this negative in front of the root. And then also print cross-validation RMSE, which is going to be an average across all of these root mean squared errors. So I'm going to take -1 times cross-val errors, and I'm going to take their Oops, cross-val errors not found. And that's because we called it cross-val errors. Okay. And so now we get an error metric associated with each individual fold. So the first fold had a root mean squared error of 184 when it was left out as a test set or a validation set. The second fold, 173. Third fold, 166. Fourth fold, 182. These are all different test RMSEs. So they're errors on different test sets. What happens is then we average those together to get a more stable error estimate. So our model, if we just used linear regression and only allowed it to see the number of reviews per month when it was predicting the listing price of an Airbnb listing in New York City, would have a really high RMSE. So we'd expect this model to do really poorly. Now let's move forward and try to add another numerical predictor. What we're going to do from here is we're going to use cross-validation from here on out, because cross-validation does provide us with a more stable, more reliable, more trustworthy error metric. So I'm just going to copy and paste that code. What I'm going to do is also look at train.head. Let's just look at the first row of the training data to see what we have access to for predictors. So let's add another numerical predictor. In fact, let's add a bunch of them. So let's add the minimum number of nights, number of reviews, the reviews per month, the calculated listings count, and the availability. So let's add all of those things to our model. So we had reviews per month. Let's do minimum nights. Let's do number of views. Let's do calculated post listings count and availability 365. So now we're allowing our model to see actually quite a few columns. So it's able to see all of these things as it tries to predict price. So now we have a new model. That new model is a linear regression model, but it's allowed access to a lot more information. So let's now build this model. We'll use cross-validation actually to build 10 models and assess those 10 models. What we're looking for is, can we build a model that has a better root mean squared error than our first one did? So our first one, when we make a prediction, we're expecting that prediction to be off by about $215. Can we reduce that uncertainty with a better model? That's what we're trying to do now. So let's take this linear regression model to predict price that has access to now not one column, but 5 columns. And let's score that model on 10 different folds to get a new error estimate. And so even this model that's allowed to see lots of information doesn't do much better. So it's got a $213.50, 51 cents is the cross-validation error estimate. Now, that's about $1.50 better than our first model that had access to almost no information. So we've made some gains, but not really great gains here. Let's see if we can get gains by using a categorical predictor. So what do we do with that? We're probably going to be better off at this point by not listing out all the columns we need, but instead dropping the columns we don't need. But for the sake of consistency, let's just continue listing out the columns that we're working with. So I'm going to keep, actually, I'm going to keep all of this code. Not much of it's going to change. It's just going to be the first couple of lines here. Um, what we're going to do is add some columns to the training features. So what can the model actually access? So we can do xtrain.head again, n equals 1, because we really don't care to see what's underneath. Oops, we want just train.head. We don't really care too much to see what's underneath those columns. We just want to see what the columns are. So far we've left out latitude and longitude. There's a reason for that, and the reason is essentially that they're encoded up in these neighborhood variables. We have neighborhood group Brooklyn, neighborhood group Manhattan, neighborhood group Queens, neighborhood group Staten Island. We also have room type private room and room type shared room. What I'm going to do is be a little bit lazy, and since to add the room type to the model, we'd only have to add 2 columns. Let's do that one. So let's add in room type private and room type shared to our model. So now our model not only gets to see all of those numerical predictors, but also gets to work with the room type predictor. Again, we're predicting price. That's not changing. We're using a linear regression model. We're going to use cross-validation to score it, because our goal at this point is just to see what class of model and which features it should have access to in order to give us the best expected predictive performance. So we'll run this again, and we've knocked the cross-validation RMSE down a little bit more by about $10 this time, but we've still got a pretty high cross-validation error estimate. This is much larger than what we would hope for, especially like we said, when the average listing is only $150. So there are some listings in here that are probably very, very high price that some good exploratory data analysis would have kind of enlightened us to. Those high priced listings are really influencing our model fit, and perhaps doing some work with those properties may really help drop this root mean squared error estimate down. But again, for the sake of this notebook and this video, let's not go there, and let's just continue thinking about different types of models and how we know one model is better than another, and how we take then our best model and fit it on an evaluation set and submit to Kaggle. So at this point, let's build another model, but another model that includes all of the available predictors. So a model including all of the available predictors. Let's see what that would look like. I just want to open up again train.head. Let's look at the first row. I want to make sure we're not going to land ourselves in any trouble here. So this is a model that will use latitude, longitude. Right now, if we don't do anything, it will include price, which is not what we want to use to predict price. That would be unfair. Minimum nights, number of reviews, reviews per month, all of these pieces of information we want to allow the model. Okay, so how do we do that? What we're going to do is, instead of listing all of the columns that the model is allowed to see, let's just say, hey, model, there's one column that you're not allowed to look at, and that's the price column. Because if we allow the model to look at the price column, then the model will ask the model, hey, can you predict the price of this particular Airbnb listing? The model will say, yeah, no problem. It will look at the price and then just tell us what the price was. That's not going to be useful for new listings at all. So let's drop the price column and store all of the other available features in this X data frame. and the response in Y. We'll still deal with linear regression for now, and let's use cross-validation to score this model. Let's see how well we do. Okay, and we've done, again, a little bit better. So we've gotten now down to a $200 RMSE. So far we've gone through a few models. We started with just one predictor, only allowing our model to see the number of reviews per month. We had an expected error associated with that model. Our goal is to reduce the error, or the expected error, in predicting the Airbnb price listings. And we've done that. We've done that a few times. So adding some more numerical features to the model reduced the expected error rate slightly. Adding one of the categorical variables reduced the expected prediction error a little bit more, by about $10. And then allowing the model to see all of the columns except the one that it was trying to predict helped us drop the RMSE even a little bit more. Let's see what happens when we work with different classes of models. So let's look at a tree-based model. So using a tree base, so we can actually just reuse all of the code that we had up to this point. I'm actually going to give the tree access to all of my model, all of my available predictor features. Instead of a linear regression model now, I'm going to use a decision tree regressor. And we'll run through the same thing. So we're going to use cross-val score on this to give ourselves a stable error estimate. That's, again, estimating how much error is associated with predictions coming out of our model. And let's see how a decision tree does. So the decision tree doesn't, actually, we didn't see how a decision tree did. So we do need to change in cross-val score the model that's being fit. So a decision tree takes a little bit longer to fit, and we do much worse now. So if we allow this decision tree to make predictions about listing prices, these predictions are going to be off on average by about $272. I want to show you something kind of interesting here. And that is going to be what happens if we use a decision tree with the validation set approach. So I'm going to go back to our first model where we use the training and test set, and we computed the training and test errors. And let's see what those training and test errors look like in terms of our tree-based model. So here, the tree that we're building is allowed to see everything except the price variable. So when we go to make predictions, I'm going to make sure that the model gets to see everything except the price variable. And I'm going to do the same thing with the test data. Drop price, axis equals 1. And we're not going to use the linear regression model. We're going to use the tree regression model. And now let's see how this decision tree regressor does on the training data and on the test data. And we need a fit call, treereg.fit on X and Y. So here are X and Y at the top of our cell. Again, X is the features that the model is allowed to look at in order to predict the column that is stored in Y. So all of the information that the model can use to predict price. And now we see why our model is so bad. This model learned everything about the training set. It learned so much about the training set that the model was useless in predicting anything having to do with brand new observations that it hadn't seen before. And that's why we're seeing such a high cross-validation error associated with our tree-based model. Watch what happens if we use some control on the decision tree regressor. So I'm going to copy the decision tree model, but I'm going to change just one thing. So now a tree model with constrained depth. So the only change I'm going to make is here inside of where we're creating the instance of the decision tree. And I'm going to say this is going to be a decision tree, but its maximum depth is going to be, let's say, 4. So it's only allowed to ask 4 questions along any of its branches. And now let's score this decision tree. And we see now that this decision tree has become competitive with the linear regression model that we had before. So our best performing linear regression model had a cross-validation RMSE of $200.99. And this tree now has a cross-validation error of $200.92. A question at this point is, why did you choose a maximum depth of 4? We had no reason to do that. And you're exactly right. So what we can do, and this is a big advantage of cross-validation, is we can use cross-validation to help us decide what the appropriate depth should be. So watch this. I'm going to copy and paste our code from above, and let's automate selecting the appropriate tree depth. And I should not say appropriate here, but maybe best or optimal tree depth. We're going to have to use a computing trick with this. So let's say let's say max depth is going to be a list of items 2, 3, 4, 5, 6, 8, 10, 12. I've got lots of maximum depths that I want to explore, ranging from really shallow trees, pretty deep trees, allowing 12 questions to be asked along each branch. And now I'm going to say for depth in max depth, I'm going to build a decision tree regressor, but I'm not going to require the maximum depth to be 4. I'm going to set the maximum depth to be depth. So as I'm moving through this list, the first chosen depth is going to be 2. So I'll set a decision tree regressor whose maximum depth is 2. Then I'll use cross-validation to score that decision tree regressor. I'll print out a little bit of extra information this time with maximum depth. I'll print out depth. So the first time this code runs, I'll print out with maximum depth 2. I'm going to make this a little bit more readable. I'm going to tab the next print lines in. So we'll be able to see which old RMSEs and cross-validation RMSEs belong to each tree depth. And then when I hit the bottom of this for loop, I'll come back to the top and I'll switch to the next depth. So the next time through the code, I'll have a maximum depth of 3. I'll create an instance of a decision tree. The maximum depth will be constrained to 3. We'll run cross-validation. Then we'll print out that the maximum depth is 3. We'll print out the root mean squared error on each of the folds, and we'll print out the cross-validation root mean squared error associated with a depth of 3. Then we'll move to 4, and we'll keep going through this entire list. So we'll let this run. We can see with a maximum depth of 2, we have a cross-validation error estimate of about 204. With a maximum depth of 3, about $202.85. With a maximum depth of 4, it's 205. Then 201 at a maximum depth of 5. Then we move to a maximum depth of 6, and the cross-validation root mean squared error, that's the expected prediction error from our model, starts to climb: 214, 231, 248, 254. These are trees that are overfit. The best tree seems to be a tree whose maximum depth is 5. According to the cross-validation root mean squared error, this is a tree that makes the lowest error. And so now let's fit that tree. So what I'm going to do is copy our old code from fitting a decision tree whose maximum depth was 4. I'm going to fit this one at 5, and we can see kind of about similar results to what we were expecting before. Let's use now maybe an advanced model, so using a random forest. So with a random forest, this is a collection of trees, which is going to be used to make predictions. What we can do now is we can use cross-validation. Again, I'm going to use this trick to help us determine sort of the depth of the tree, and perhaps the, so we can see this gray box shows up with lots of parameters that we can use. So the maximum depth, the minimum number of samples per split, the minimum number of samples per leaf. You can go to scikit-learn's documentation on random forest regressor to see what each of these means. Right now, what I'm going to do is set the, let's say, minimum samples split to 5%. Actually, let's do this. Let's do max depths. Actually, let's just do the same thing. Let's constrain only max depth, and let's let this go through exploring different depths for trees. So we have random forest regressor. I'm going to rename this to RF reg. We're going to run cross-validation on our random forest. We'll print out the maximum depth for the random forest. We'll print out the test RMSE on each fold, and we'll print out the overall cross-validation error. This is going to take a little bit longer to run because we're going to be building thousands of models. So while this is running, I'll just talk to you a little bit about what we've done up to this point. We started out with a simple linear regression model that used a single numerical predictor to predict price. This was the definition of that model. So we had X, which stored the data frame containing all the predictors that the model was allowed to see. It contained, then we had Y, which contains the truth, the responses that we're trying to predict. Then we defined the model class. Everything above here was the instructions for fitting, for essentially building the model. So this is what the model is allowed to see. Then we fit the model, and in this first code cell, we used the traditional validation set approach, where we fit on a training set and we estimated the true prediction error by making predictions on unseen test data, and then using the root mean squared error to estimate the prediction error. We saw that the training root mean squared error was lower than the testing root mean squared error. That's to be expected. What we're doing now is we're trying to search for models that will have a lower root mean squared error on held out data. So on observations that the model didn't get to see during training, how poorly are our model's predictions? We saw that our model is really performing quite poorly. And we had highlighted earlier that perhaps some Some initial data exploration would be helpful here because there are probably some very highly priced properties in this data set that are skewing our model's results. Um, from that point, we looked at not fitting a brand new model. This is the same model, but instead of assessing it via the validation set approach, where we just have one validation set and we get one test error, by assessing it on multiple validation sets through cross-validation. So we used 10 folds. That resulted in 10 models being fit and 10 test errors being estimated. So here are those 10 test errors. And then we averaged those test errors to get a more stable error estimate. So for this same model, we get a new error estimate that's a little bit more stable and more reliable. So if we built a model and used it, where our model was only allowed to look at reviews per month, when it went to predict price, we should expect that model to be off by around $215 when it makes a prediction. Then we looked at adding other predictors. So we added all of the numerical predictors we had available to us to our model. So again, here's the definition of the model. This model gets to look at more information when it goes to make those predictions. We use cross-validation to estimate the expected prediction error for that model. And we found out that using more information was in fact beneficial, not super beneficial. We dropped the estimated cross-validation error here by about $1 just by adding some more information to our model. Then we considered what might happen if we allowed our model to see some of the categorical data that was available to it, and we added the room type to the model. So again, here is our model definition. It's allowed to see all of the variables that we've allotted to X. So all of those columns that we've allowed to be stored in X from the training data. And we're still predicting price. That hasn't changed through any of this. And at this point, we were still using a linear regression model. Again, we're using cross-validation to generate an expected prediction error for that model. So if we were to use this linear regression model to predict price, and that model was built so that it had access to all of these columns, then we should expect the model's predictions to be off on average by about $204.20. So still not a very good model. Then we took a look at what might happen if we allowed the model to see every predictor available to it. So the only thing we're not allowing our model to see is price here. Predicting, so we're not allowing the model to see price, but we're asking it to predict price. We're still using a linear regression model. We're still scoring it with cross-validation, but remember, this is just getting us an error estimate. So if we used this model that was allowed to see all of the predictor columns, how might we expect that model to perform on new data? And if we if we use that model to make predictions on new data, again, we'd expect that model to be off on average by about $201. So this model does the best out of any of our linear regression models that we had built prior, but it's still got a really high error rate. Or here, we shouldn't call it a rate, but an error estimate. The average error our model makes is big. Where we went from here was we looked at a different class of regression models. So we looked at a decision tree. Again, the form of the model is not so different. In X, we're storing all of the columns that we're allowing our model to see. For a tree, that's all of the columns that the model is allowed to ask questions about. And so our model is allowed to ask questions about any variable other than price as it tries to predict price. Then we're going to score that model using cross-validation, which gets us a pretty stable error estimate. That's an expectation for how well or how poorly our model will perform. And if we look at the cross-validation error estimate, This is how an average, and so it's a more stable error estimate for new data. And so this tree did very, very poorly compared to any of our other models, which perhaps was a little bit surprising. It does even more poorly than the model that was only allowed to ask about reviews per month. And then we highlighted that, well, if we look a little bit deeper into this tree-based model, the problem is not that the model itself is bad. The problem was that we allowed the tree to learn too much about the training data. So the tree learned so much about those properties in the training set that it knew exactly how to predict the prices for those properties, and it made no error whatsoever on the training data. So this model is way overfit. And when we asked that model to make predictions on new properties, it did super poorly. So it learned way too much about the training data, and that model had no utility on new properties that it hadn't seen before. So at that point, we looked at constraining the depth of the decision tree. This is restricting the number of questions the tree was allowed to ask. We allowed the tree to ask 4 questions along any branch, and we saw that we got pretty comparable um, performance estimate. On average, our tree at a maximum depth of 4 questions was off by about $201 when it made predictions. And then we had highlighted that, well, there was no reason really to choose a maximum depth of 4. And we can use cross-validation to somewhat automate the selection process for us. So we can assign a list of maximum depths that we're interested in exploring, fit trees with those maximum depths, estimate the prediction error associated with those trees. And then once we had those estimates, we could look at the cross-validation error each time and try to identify what the best depth was. The best tree depth was the one that minimized the cross-validation error. And it looks like here, a tree with a maximum depth of 5 had the best cross-validation error out of any of the trees that we built. In particular, once we allowed the tree to ask 6 or more questions, the tree began to fit worse, to make worse and worse predictions on new properties. So we saw that cross-validation error rise, and this is evidence of overfitting. We refit our tree on that optimal maximum depth of 5, and again, we got pretty comparable, uh, comparable error estimate for that tree. Then we used this advanced technique called a random forest that took quite a while to fit. But we see with a maximum depth of 2, we fit a random forest. That collection of models together made an average prediction error of $204. The maximum depth of 3, we're down to 201. The maximum depth of 4, we're down to 200 and a quarter. And then with increasing maximum depths, we're starting to rise. With a maximum depth of 8, we're down a little bit to $200.13. With a maximum depth of 10, we're back up to 201. The maximum depth of 12, we're down to 200. So it seems like we're getting really comparable performance from all of the trees whose maximum depth is at least 4. So what we could do at this point is come back and fit a random forest whose maximum depth was 4 and see what performance that model gets. So still, we're going to allow the model to see all of the columns in our data set and still predict price. We're going to define a random forest regressor. This is going to be, again, random forest regressor. And the maximum depth, we didn't see any real gains once we moved on to maximum depth of 4. So we're going to define that here. Maximum depth of 4. We'll run cross-validation again just to see what the error is on this. And we get, again, around $201.80. So all of the models that we built seem to have performed pretty comparable to one another. We weren't able to knock the prediction error estimate down below $200. Again, doing some exploratory analysis at the beginning of this would have perhaps helped us. So I'm just scrolling through now looking for what our best performing model was. So the linear regressor that did best had a $200.99 cross-validation error estimate. The decision tree with a constrained depth of 4 was at $200.92. Once we optimized that, we actually had worse performance. Looking then at a random forest, we were at $201.80. So it looks actually like maybe the linear regression model that used all of the predictors was the best one that we had access to. So let's move forward with the linear regressor using all available predictors. So I'm going to go back in the notebook and grab that model. The linear regression model with all of the available predictors, here it is. I'm going to grab everything there. We're not going to use it all, and we're going to actually change a couple of things. I'll highlight that. So instead of running cross-validation at this point, what we'll do is we'll fit this model, linreg.fit x, y. So this is fitting on all of the training data. If you wanted to at this point, you could add the test data back in to just give yourself more data to estimate those coefficients. That's not a bad idea to do. I'm not going to do it here just for time, but let's fit the model. Now we have that model fit and we can use it. But what's important is we need to look at X and we need to look at eval. And I'm going to do n equals 1 again here. And we need to make sure that X and eval contain, we don't want eval. We did some preparation with this. We had eval reduced dummies. So actually, let me show you eval for a second. So before we do this, if I tried to apply my model to the eval data set, my model is going to get upset because my model only knows about the latitude, longitude, minimum nights, number of reviews, reviews per month. All of these columns in X are what my model knows about. So if we try linreg.predict on eval, the model is going to say, hey, I didn't know actually about the host ID or host name or ID or last review or name. I knew about none of these columns, and now you're giving them to me. Also, in order to make a prediction, I need to know about these columns: neighborhood group Brooklyn, neighborhood, and I don't have them, so I can't make predictions. So if the data frame that you're trying to make predictions on doesn't have exactly the same columns as your model was fit on, your model is going to complain. And so what we need to do is look at eval reduced dummies. Now, eval reduced dummies has a latitude column, and so does X. It has a longitude column, and so does X. Minimum nights, number of reviews, reviews per month, calculated host listings count. Just going to continue moving these across. Availability 365, neighborhood group Brooklyn, neighborhood group Manhattan, neighborhood group Queens, neighborhood group Staten Island, room type private room, room type shared. These data frames have exactly the same columns, and so now I can make predictions on this new data frame. Well, reduced I made a typo in there. So now eval reduced dummies can be used to make predictions from my model. Input contains NaN infinity or a value too large for data type float 64. So we have some problems, it looks like, in eval reduced dummies. Let's take a look at those. This is going to bother me, so I'm going to do just a rename, eval reduced dummies, equals that. And now eval reduced dummies uh, I think the problem we're going to have is the same problem we had with the original data. So .isNA.sum. And okay, so reviews per month has a bunch of missing data. And so let me keep that. That's worth keeping. And so what we'll do is we'll say eval reduced dummies, where eval reduced dummies number of reviews is NA. So I'm going to look at all the entries where that information is missing, and I'm going to drop in 0. And now we'll do eval reduced dummies.isNA.sum. We should now have zeros. Oops. We want, okay, I am going to come back here because I overwrote entire rows of the data set with zeros. I didn't want to do that. So I want to only overwrite number of reviews. So look at this number of reviews column. Only take a look at the entries in that column where the information is missing. And in those entries, let's put a 0. Now let's see. Okay. Reviews. Okay. Value is trying to be set on a copy of a slice of a data frame. All right, so let's try here where we did this renaming. Let's just make a true copy. Now, eval reduced dummies. We're going to look at number of reviews. We're only going to look at the entries where that number of reviews was missing. Let's put zeros in there. Oh, because it's not number of reviews. It's reviews per month. Reviews per month. Reviews per month. So where I just went and made a true copy, that should have been, that's unnecessary. I was trying to replace the wrong column. So now we see that we're not missing any data anymore. And so we should be able to come back to where we were making predictions. I'm going to copy that and just move it down into the notebook here. Again, we get missing data. Oh, because I'm trying to use the wrong data set. And there we go, we get predictions. So again, the big thing with getting predictions is ensuring a couple of things. One is that the data frame you're trying to make predictions on has exactly the same columns as the data frame that your model was trained on. So that's the big thing that you need to make sure of. We had some issues when I tried to make predictions here because we had some missing data that we hadn't taken care of earlier. At this point, if you're thinking about the competition assignments, you're being asked there to create a data frame of your predictions to make a submission to Kaggle. I think we're going to do pretty poorly because we didn't do any exploratory analysis here in this competition. But let's make a submission. So submission df is equal to pandas data frame. We're going to look at the sample submission here to ensure that we build the right data frame. I need an ID column and I need a price column. I'm going to ask for ID. And the ID I'm actually going to get by going to the eval data frame that we originally had and grabbing its ID column. And then the price column is our model's predictions. So predictions. I'm going to get rid of this. And I'm going to look at submission df.head. And there we go. So we can see 243.11 was the predicted price for the first entry, 225.07 for the second entry, and so on. So now we have our predictions. Let's get this out as a CSV file. So the way we do that is with submission df.to CSV. We're going to call this, let's say, submission.csv. And by default, what would happen is we'd save out a comma-separated values file, but that comma-separated values file would have not 2 columns, it would have 3 columns. So by default, we're saving out the index 2. It would be an unnamed column. We don't want that because that index was not present in the sample submission file. So we're going to set index equal to false, which will prevent that 3rd column from being saved out. We see that code cell ran okay, and if we come here to refresh, we see submission.csv. I'm going to download that, and then let's see what happens if we make a late submission here to this sliced competition. So this is submission 1 is what it downloaded as. Multiple linear regression model with lots of predictors. Let's make our submission. Our submission is being scored. Our score was 0.69. That does a little bit better than the benchmark, but not better than the majority of the competitors here in this competition. They were able to get down to 0.4. Remember that these error metrics being used in this competition are not the root mean squared error. This is a different error metric that we weren't optimizing. All right, so I think that's going to be it for this video. I'm going to stop sharing my screen. And so hopefully you found this helpful. Again, this has been a video showing you how to build a variety of models. We highlighted that when you use cross-validation, you're not actually building a brand new model. Cross-validation is not a model type. It's just a strategy for estimating a more stable error estimate. And so it's getting more accurate performance estimate for your model is what it's doing. What we did is we built a handful of models. We identified a model that had, we thought was the best error estimate we could get. Then we used that model. We did a final fit on it. We made predictions on the evaluation data, and we submitted those predictions to Kaggle for study. So again, I hope you found this helpful. Thanks, everyone, and I'll see you next time.